Okay, very nice. Okay, so good evening in Taiwan and good morning in Sao Paulo, Brazil. And today is really my great pleasure to welcome Dr. or Professor, quasi Professor, almost Professor, Eddie Nijholt, from what is your institution now?
Yeah, USP, ICMC. Yeah.
ICMC, yes, ICMC. And today he's going to tell us his ideas and research on the so-called exotic symmetry in network dynamic systems. And we are very curious about this. And we hope that after his talk, these symmetries are not exotic anymore to us. Okay, so let's welcome him.
Right. So thank you very much for the invitation, and thank you very much for listening. So yeah, so welcome to my talk on exotic symmetry in network dynamical systems. So there's quite some words to unpack here, right? So there is this exotic symmetry, whatever that will mean, and network dynamical systems. So let me start with the part about network dynamical systems. So for me, a network dynamical system is really an ODE, or an ordinary differential equation, or a class of ordinary differential equations. So a structural class of ordinary differential equations motivated by a given network. So here is an example of what I would call a network. Essentially, it's just a directed graph, right, with a bunch of bells and whistles. So what you can see is that some of the nodes are round, so they are of the same type, of the round type. Another node here is square, so this would be a node of another type. There are some connections between them, some interaction, and they have different colors and setups, and that just means that they could be different kinds of interaction between the nodes, or similar kinds of interaction. So you can think about maybe this model's an ecosystem, and the round ones could be prey animals or populations even of the same animal, whereas the square one might be a completely different animal. And then maybe the red arrows here are competing for space, whereas this is a predator-prey relation. So you should sort of think about it in that way. Or it's different computers that have, different kinds of, different types and different ways of interaction. But so it's really, a network is really just a directed graph with some bells and whistles, some types. So associated to it, like I said, there will be a class of ODEs. So what I've done here is there's a very easy way to go from the left to the right, and essentially all the information that's in the right is also in the left. So what I've simply done is I've taken each of the nodes and I've given them variables. Can you see the little hand, by the way, on the slides? Okay. So
yes,
what I've done is, perfect, thank you. So what I've done is I've associated variables to the nodes, and I've given them response functions. That's sort of how they see the world around them. And then I've simply plugged in all the variables corresponding to these arrows. So for instance, there is some kind of a relation, some kind of an interaction from node 1 to node 3, which is this double-headed green arrow. And that's why I've put an x1 here in the equations for y3 dot. So the dot is, of course, just time derivative, right? We're just doing ODEs. And you have to be a bit careful with the phase spaces, the domains and the codomains. But if you fix that and you let f and g vary, you have a whole class of ODEs that somehow captures this interaction structure. We call these the admissible vector fields. We typically call them admissible vector fields for the given network. So I'm interested in these kinds of objects. I'm interested in their behavior. So you might wonder why, right? Why are we interested in these kinds of systems? Why not ODEs of a different structure or just general ODEs? So there are essentially two reasons for that, depending on where you're coming from, right? So first and foremost, network dynamical systems, they show up everywhere in nature, right? Think about models in neuroscience, think about trying to figure out the intricacies of social media or ecosystems, like I said, or certain computer protocols. Networks are everywhere. And essentially, they even show up where you wouldn't immediately think of them. So like whenever you're not modeling from first principles, very often the information that you can put in your model is what variables talk to what variables and which ones really do not. So this is why they even show up as models in, say, climate studies, right? So they are very important just in terms of modeling assumptions. But another reason, just purely from a mathematical point of view, it turns out that network dynamical systems, they show a lot of interesting dynamical behavior. So by interesting, I will mean things that are very plentiful in network dynamical systems that are essentially unheard of if you just look at the class of structureless, say, ODEs on Rn. So let me give you some examples of that, just some motivating examples of what I mean. So here I have another network. Here all nodes are of the same type, so I've placed the same response function f here, but other than that, right, it's just the same rules that we had before. I've chosen this example because the three things I'm about to mention are a bit clearer in this example. So the first thing that you notice when you start playing with these systems is that it has a lot of invariant spaces, so flow invariant linear spaces. So by flow invariant, I mean if you initiate on this linear subspace and you let time run, right, you stay on it, both forward time and backwards time. So when you put x2 equal to x3, then you see that the equations for x2 dot and x3 dot will be the same. So indeed, you stay on this linear subspace, and the same when I set x1 equal to x2 equal to x3. So this is quite a trivial observation. I mean, you can just plug it in and see that it's invariant. But again, I want you to think about general ODEs, right? General structureless ODEs. You will never ever find a linear subspace that is flow invariant, right? This is very anomalous. Whereas here, it just comes up naturally. And also notice that whatever f I choose, even if my f is, not even C1, right? Whatever f I choose, these are invariant subspaces. Now, of course, I'm not just mentioning them without reason. They are heavily associated with this concept of network dynamical systems, which is called synchronization, right? The idea that the phenomenon that multiple cells start doing the same thing, which is a hot topic in network dynamical systems, and it has everything to do with these spaces. It has to do with being on these spaces or going towards these spaces. So that's already kind of interesting. That's already quite anomalous when you restrict your attention to network dynamical systems. Slightly more interesting, perhaps, is degenerate eigenvalues. So when I take f to be linear, right, say just linear from R4 to R, and I write this corresponding system down in matrix form, then the matrix will look something like this. So A is then the derivative of f in the first component, B in the second one. And if you write that out, you will see this. You could also think about this as a Jacobian of such a system at 0 or at a point x1 is x2 is x3. So they're relevant for the dynamics, of course. And when you look at the eigenvalues, you will see that there is one eigenvalue, a plus b plus c plus d. That one's easy. That's just the constant row sum, which is, of course, a consequence of having a system like this. But you will also see an eigenvalue a that is always there twice. I mean, it's always twice unless it's, unless b plus c plus d is 0, then it's there even thrice. But you always have a double eigenvalue. And generically, the algebraic multiplicity will not be the geometric multiplicity. So you have a non-trivial Jordan block. Again, this is a consequence of the form. It doesn't depend on what A, B, C, and D I choose, right? So in that sense, it's generic. It's even just always true. But it's, again, highly anomalous, of course, if I just take a random 3 by 3 matrix to have a double eigenvalue. And related to this is, of course, the topic that we will mostly be interested in this talk, which is that of unusual bifurcation scenarios. So I'm not expecting everyone here to be fully familiar with bifurcation, so let me just quickly introduce that. So the idea of a bifurcation is you introduce an extra parameter, an external parameter that you're allowed to change. So think of it as like a dial. You have an ODE, but you can change some specifics. And then you're interested in seeing how the dynamics changes, right? So you want to know not just, you know, changes in the numbers, but really qualitative changes. So in my example, again, I want to introduce a parameter. So that's this lambda. But it's important for me for this system, for this setup, that I don't leave the class of network systems. So that's why I've put in it here. For every fixed value of lambda, I have a network ODE corresponding to that same network that I showed. And then I'm interested in seeing how the dynamics changes, right? When this dial is moved. And you could just be interested, it already becomes interesting when you're just asking this about steady states, right? So fixed points of the dynamics. And when you do that, it turns out in general, for general ODEs, you almost always see this scenario. So this is what we call a saddle node bifurcation. So this is what I've pictured here as just steady states of the system. Here's lambda, so every vertical slice is one ODE of this form, which, you know, may or may not have some steady state points. This is just some x is just could be x2 or x1 or x3 or some combination, some sufficiently generic combination. And what you see in the saddle node is as you move your lambda, there are first locally no steady state points, and then two emerge, typically a stable and an unstable, or at least one has more stable eigenvalues than the other ones. And this bifurcation, this saddle node steady state bifurcation, is important because you can prove that if you take a general ODE, so just a generic ODE without any additional structure, right, without necessarily a priori any additional structure, then this is the generic bifurcation scenario. Now, I will not go into what generic exactly means, but typically you should think of, there are some Taylor coefficients, some combinations of Taylor coefficients. These could be zero, but typically they're not, right? They have no reason to be zero. When they're not zero, this is what you see. So in that sense, it is generic. The chances are zero that you ever see something else. But that is, of course, in the class of, say, all ODEs and Rn. What happens if I restrict my attention, if I ask the same question for generic bifurcations of systems of this form? So I have the same f and I plug in the variables in some prescribed way. Turns out there are two scenarios. Again, either this one, which has something to do with that eigenvalue a plus b plus c plus d that we saw, but equally generic is something completely wacky, something completely unusual, unheard of for general systems. So here's the corresponding table for what's happening here. So essentially two steady states go in and four come out, or the other way around. There's always, you can always have lambda goes to minus lambda and see the other picture. Some of these branches are fully synchronous, right? One is fully synchronous, one is partially synchronous, where x2 is x3, and this branch over here has no synchrony whatsoever. Stability goes from fully synchrony to not synchronous, so this is a fully synchrony breaking bifurcation. But of course, even if you don't know that, just seeing this picture, this is completely unheard of for general systems, general ODEs, and it's generic in this class. So that really tells us that something interesting is happening when you introduce a network structure. So when you have that as your modeling assumption, chances are you're already capturing something unusual. So of course, people want to understand this. There's a rich history of trying to understand bifurcations and trying to, for instance, classify these or just calculate what the bifurcation is. But it turns out it's not so easy when it comes to network systems. So let me tell you a little bit about the main challenges. So this will be a bit of an abstract slide, and then I'll give a very concrete example, which will motivate really a technique that will motivate the rest of this talk. But what is the main challenges? Well, from a very abstract level, when you look at bifurcation analysis and really many techniques, many established techniques in dynamical systems theory, you will see that it involves coordinate changes. I mean, this should come as no surprise. If you're doing normal form theory, you're using coordinate changes to make your system in a nice form. Or you might identify some invariant space on which the dynamics are nice or the dynamics are interesting, and you might want to flatten that out, and that's a coordinate change. So coordinate changes galore, but the problem is coordinate changes will typically not respect your structure of nodes and connections. You have some nice variables corresponding to the states of your nodes. You're interested in these variables. You want to know which variable talks to which variable, which ones do not. You're interested in questions of synchronization. So when are two nodes the same? So when are these two of these variables the same? And when you just take coordinate changes nilly-willy, you are now not talking about the state of node 1 anymore, but your coordinates will be the state of node 1 plus 17, the state of node 3 plus the state of node 5 squared. So there's no notion of nodes and connections anymore. And in other words, as a consequence, your entire network structure is lost. And this whole talk started being interested in the impact of network structure. It also means that all these aforementioned techniques are essentially at this point almost useless in the network setting, at least unless you do something very clever and very case specific. And so we need new techniques that we either need new techniques that can deal with networks, or maybe rethink the idea of networks completely. So the solution that I'll present will be somewhere in between this, as will be clear later on. So let me just give a very concrete example of a technique that seems to fail quite badly when it comes to network dynamical systems, but I will actually tell you that it's not so bad. So the technique that I will mostly be interested in this talk is that of center manifold reduction. So just to give you the idea of what center manifold reduction means, it's heavily motivated by what happens for linear ODEs. Even though it's not a technique for linear ODEs, it's heavily motivated by what happens there. So suppose I have a linear ODE, x dot is A of x. So A is just an n by n matrix. Then it's known that A induces a splitting into subspaces of your phase space, EC and EH. We call them the center subspace and the hyperbolic subspace. Now, this splitting is uniquely defined by the property that A leaves both of them invariant. So A maps elements of EC to EC and EH to EH, and A has only imaginary eigenvalues on EC, right? So only eigenvalues on the imaginary axis when you restrict it to EC, and it has only eigenvalues away from the imaginary axis, of the imaginary axis, when you restrict it to the hyperbolic part, hence the names hyperbolic and center. So when you kind of look at it that way, when you consider that splitting, essentially what you're saying is that the ODE x dot is AX has just boring exponential growth or decay in the EH direction, and all the interesting solutions, so any additional steady states or any families of steady states or families of periodic orbits, if they exist, they would all be on EC, right? So this is the picture to have, all exponential behavior in the EH direction. And if there is something interesting, you could argue how much interesting stuff is there in a linear system, but if there is, it's all on that EC plane, right, subspace. So people started asking, okay, what about nonlinear ODEs? So suppose I have an ODE I can see it as a, maybe big perturbation of a linear system. So I add nonlinearity, think of them as quadratic terms or higher, right? And then I can start asking the same question. Is there still some invariant manifold, some invariant space that has all the interesting stuff? And it turns out, under some assumptions, there is. So the theorem, more precisely, is that given the A, given some regularity, there exists an epsilon, right? There's always an epsilon. There is some analysis going on, such that if your nonlinearity satisfies some nice bounds, that we will not be interested at all in the rest of this talk, but okay, you need some bounds, then there exists a CK map from the center space of the linear part to the hyperbolic part, such that the graph of this map is flow invariant for the full nonlinear system. Furthermore, it contains all bounded solutions, and this MC is in fact, this graph is in fact tangential to the center subspace. So we call this the center manifold of the system. And so this is the picture that we had, and this is the picture that you now have, right? So there's now a graph lying over EC, but other than that, you still have that all the interesting, all the bounded solutions, they are now on that MC. And, the dimension in particular is just that of EC. So I'm putting the in quotation marks because you always have to be very careful talking about the center manifold of a system. There are typically many, but if you satisfy these bounds, if you have this particular theorem holding, then you can put your finger on the canonical one. So that's what we will call the center manifold. There will be something that pops out of the contraction argument, and I will refer to that as the center manifold of the system, even though you always have to be careful with that. So this is a very important result because this can be a major dimension reduction, right? Because maybe your whole system is 1,000-dimensional, but EC only corresponds to those eigenvalues that are precisely on the imaginary axis. So this might be just 1, 2, or 3-dimensional. Then you can still just do bare hands analysis. You can just do calculations, whereas for a 1,000-dimensional system, there's no chance. So, all right, so center manifold reduction is one of these techniques that are very powerful, and we wish we had at our disposal when we're doing network dynamical systems. But the problem is as I laid out, right? So suppose I have some network dynamical system, doesn't really matter which one. Suppose I have the phase space. Suppose I find a center manifold. Because of the fact that this contains all the interesting stuff, all the bounded solutions, right? Maybe homoclinic and periodic. I want to restrict my attention to just this subspace, this submanifold. So I just project it down, right? Remember that this is a graph over EC. So I have a very nice chart, just project it down. And so I am now interested in what's going on here. This is my dimension reduced system. But, now we have a problem, of course, because what is this? Is this still a network vector field? Well, this cartoon heavily implies it's not because it's 2-dimensional. If it is a network vector field, it will be for another network because, this has to be at least 3-dimensional. If this is honestly 2-dimensional, something's going wrong. So maybe it's something else. Maybe there is still some structure that we can find, because if the only thing we can conclude is that if this is just a general ODE on R2, then we're out. Then it's game over, because we know by generic bifurcations, for instance, that some structure right will survive. There is something about this reduced vector field that contains in it somehow the information of all these unusual bifurcations. So we need to find some kind of a structure that still sits on here. But of course, there are coordinate transformations, there are weird graphs. So a priori, there is no way of finding that. And that is really the problem that we set out to solve, mainly motivated by center manifold reduction. But I will hopefully tell you, if there's enough time, that these techniques I'm about to describe, the solution I'm about to describe, also works for, say, normal form reduction or Lyapunov-Smith, even a phase reduction, which is a completely different setting, of course. But the problem is always, you do dimension reduction or you do complexity reduction, what survives after the reduction? So the idea that we came up with is that of a quiver symmetry. And just to drive home that you can really prove theorems like this with these techniques, today we will see the following theorem. So this is with Popperink and Søren van der Gracht. Say that we just have a very simple network system. Say just x dot is f of x, y dot g of x and y. So really, the only network feature here is that node 1 only depends on itself, but it feeds that information into node 2. So this is just a very easy example. It will be clear, once we get further along the talk, that we will be able to prove many more theorems like this. But this is just some very concrete, easy to understand theorem that by the end of this talk, you will hopefully believe, and we will essentially see a proof of. So consider this system, little bit of a technical assumption. Assume both f and g, their linearizations have some eigenvalues on the imaginary axis. If not, the situation becomes much easier, but it becomes essentially trivial what I'm about to say. So let's just assume both of eigenvalues there. Then the dynamics on the center manifold is conjugate to that of a system of this form. So in other words, feed-forward structure, this network structure, can be fully preserved in center manifold reduction. Same, by the way, for normal forms and Lyapunov-Smith. So, right, like I said, this is just a bit of a teaser. This is just a small theorem that we will prove. This will guide us in the examples, but it will be clear that these kinds of theorems will be easy to prove with the machinery we're about to develop. So the machinery that we're about to develop is called quiver symmetry. So quiver symmetry should really be seen as a generalization of group symmetry. So before I go into the definition, before I tell you precisely what quiver symmetry is, I really want to drive home that it's a generalization, and a very clear generalization, of group symmetry. So of dynamical systems with, just classical, say, finite group symmetry as we're familiar with. So to drive that point home, I want to convince you that group symmetry, right? What is group symmetry? Again, consists of 3 ingredients. So the first ingredient to just classical group symmetry is a group, which is an abstract algebraic structure sort of floating in the background, right? So a group is a set with a nice multiplication or addition and inverses. We've seen that in year 1 or 2. An example would be just z mod 2z under addition. So then the second ingredient for just normal regular group symmetry is a group representation. So what is a group representation again? Well, it consists of a single vector space, right? And linear maps for each of the elements. So there has to be a little bit of compatibility with multiplication. I'm not giving the definition of a group representation here, but that is just, the second ingredient. You now have a vector space to work with and some linear maps. So in this example, you would put the identity to A0. You always do that. And A1, you might.
Eddie, can I ask one question here?
Sure.
Already
No,
here.
go ahead.
So we consider linear group representation. We never consider non-linear group representation, right? Because some of my friends who study differential geometry, they always consider they always consider solutions on manifold. Then what is the main reason that the classical group symmetry and the quiver, they all consider linear maps, never non-linear maps?
Yeah, no, that's a good point. So in this, well, let me put this way. There are always there are two
Of course,
main.
if you consider nonlinear map, then of course we cannot consider vector space. It should be a many for a nonlinear map between many for diffeomorphisms. Let me call this diffeomorphisms between many. And do you know why is the main reason?
Yeah, exactly. No, there are two reasons why people consider group symmetry in the linear case, why they consider linear group representation. It's a very good point. So the first one is a result, the name has escaped me. It's at the tip of my tongue, but there is a famous result that says that locally, if you have a representation of a say a compact Lie group, say a finite group, under some regularity conditions, you can you can find a coordinate transformation that makes the group action linear. So this is, I forgot the result, but
this is called Bochner linearization.
Yeah, right? Bochner linearization, that's exactly the one. So Bochner linearization is always the first big argument for considering linear group representations. The second one is network systems. So very often if you have a network system and your graph has a symmetry, then the corresponding symmetry on the phase space is already linear because it's like changing coordinates. So it's also very natural from network systems. I will absolutely not have Bochner in my setting. So my motivation is the fact that these transformations are induced, they are motivated by the network graphs, and then they just become linear. They automatically are linear. But of course, it's a very good point because I will not have any Bochner settings. So yeah.
Okay, thank you very much. Thank you.
Yeah, no, that's a good question. So yeah, a linear group representation indeed would just be a vector space, in this case R2 and two of these linear maps, or in this case, two of these linear maps, right? And then the third ingredient to a group symmetrical system, or indeed a symmetrical group symmetrical system with linear representation, is given a group representation, it's a choice of an ODE on your vector space, such that all these linear maps send solutions to solutions. So if I, for instance, look at this ODE, and again, this is motivated by my network system, you can think of this as a network system, right? Then if XY is any solution, then so is this thing where I change the entries, then this is also a solution. So that is in a nutshell what group symmetry comes down to. So I will completely mimic this in a definition of quiver symmetry. So these three items. So a quiver, first sort of the abstract algebraic thing. A quiver is just a directed graph, which is, there's a bit of a story, a bit of a history here, why a quiver is not just called a directed graph, it's just a directed graph. And you are allowed to do essentially anything. You're allowed self loops, you're allowed multiple self loops, right, with the same node. You're allowed to have multiple connections from node A to node B. It need not even be connected, even though even in my setting, being disconnected will be unnatural, but it is allowed. It's just a directed graph, plain and simple. People even look at infinite sets of nodes and infinite sets of arrows, but that I will not do. So let's say finitely many nodes, vertices, finitely many arrows. But other than that, just a directed graph, nothing more. So this is that kind of algebraic thing floating in the background. But this is arguably even easier than a group. So then the second thing we said was a quiver representation, group representation, now a quiver representation. So a quiver representation assigns vector spaces to all the nodes and linear maps to all the arrows, and that's it. So here's an example of a quiver representation of this quiver. So what you see is that I have appended R2 to this node, R to this node, and this alpha, this arrow, gets this linear map. So there is only one rule, which is of course that right, if I have an arrow from a node to a node, then the domain has to be the vector space that you have here, and the codomain has to be the vector space that you put here. But other than that, there are absolutely no rules. So this map need not be invertible. That doesn't even make sense in this example. It need not be injective. It need not be surjective. It can be the zero map, which is actually handy in some of what we're about to do. So just linear maps to all the arrows. There's also no notion of concatenation. If you have an arrow and another arrow, then if you follow them, you can concatenate the linear maps, but there is no other arrow that has to somehow correspond to that new linear map. So no concatenation, just domains and codomains have to add up. So that is what it is to have a quiver representation. And then the third thing that we're going to have is a quiver symmetrical system. So a quiver symmetrical system for a given quiver representation of a given quiver is an assignment of ODEs to each vector space. So instead of one ODE, I now have as many ODEs as I have vertices. And the only thing that I demand is that the linear maps that we had, that we put on all the arrows, they have to send solutions to solutions. So solutions of, say, this ODE to solutions of this ODE. And since they're all linear maps, this is relatively easy to check. Sorry. So here's an example.
Can I have
Yeah.
a question? So, because of your notion of a symmetric system, so the vector space must be invariant, right? As a necessary condition. Necessarily.
The vector space is finite. Yeah, I forgot to say that. That's
No, they have to be invariant, right? Flow invariant.
Sorry, say again.
We are the vector space
Yeah.
as nodes to be flow invariant.
So yeah, you can do it. Let me think about that. Yeah, the reason.
Because
Sorry.
you send solution to solution, so necessarily the vector space must be flow invariant, right? Yes.
I think. Oh, sorry. Now I see what you mean. Yeah, exactly. No, yes. It took me a while to think about it that way. Yeah.
We cannot assign arbitrarily vector space, or
I think that's only if the ODE at the source and the target is the same. But you could have this situation, right, where Eddie has one ODE and another ODE which is the same in the first component, but strictly speaking, is a different ODE.
but they are all flow invariant in their own ODE.
What do you mean flow invariant?
Because solution to solutions.
Yes, you're sending solutions of one ODE to solutions of the other.
Yes.
But what do you mean by flow invariant?
Because this is a target and source, they are all space for the
That's the
solution.
space of the ODE.
Which means we can only consider flow invariant.
The ODE is defined, the ODE on the left is defined on R2, the ODE on the right is defined on R. But strictly speaking, they are different things, right?
Yeah, you're answering my question. The question for me. That's exactly correct.
I have to understand this because here you see R2 is very easy, but maybe they are more complicated in dedicated invariant vector space. You can assign layer, right?
This is only an ODE on R2.
Are you saying your vector space is always very large, like R2, R1, R100? There's no like X1 equals to X2 or, you know?
Oh, anything is allowed. Anything finite dimensional is allowed. Just in step 2, I just put in any vector space I want, any vector space I want, any linear map I want with the right domain and codomain. Then I just pick any ODE I want on this one, any ODE on this one, but I need that this sends solutions to solutions. But that's all there is. So you can consider the situation as far as the ODEs are concerned. You only have to look at one vertex, one ODE per vertex, but there are some conditions on the on the collection of them.
Okay, thank you.
So no, it's a good question because this is the main topic. So it's important that this is clear. So here's an example. If I indeed put this ODE over here for any f and g, and I put this ODE here, but I take the same f, then you can check that this sends solutions of this ODE to solutions of this ODE. And because it's linear, you just have to check that there's a commuting diagram of maps. I'm seeing vector fields, but it's on on the vector space. I'm seeing the vector fields as maps. You just have to check a commutativity relation for every arrow. But you can actually see that if that this always sends solutions of this system to this system. And what's more, if you take a tuple of ODEs, here one and here one, and you demand that this sends solutions to solutions, this will be the form. So this is actually equivalent. So being of this form for some f and g in the same f here is actually equivalent, you can check that quite easily, to this map over here sending solutions to solutions. So this is just an example. In general, we have to check that for every arrow, right? For every linear map that you put on an arrow. I should also say at this point that quivers and quiver representations are a big topic in algebra. This is not our invention. Number 3, as far as we know, is the novelty, is our invention, but 1 and 2 are old and established, and they're not our invention. So why quiver symmetry, right? Why am I interested in this? Because remember, I came from network dynamical systems. So it turns out that quiver symmetry actually captures a wide array of network properties. So here's a list. Here's a list. I will go through some of them, but I just want to highlight a couple of them here. So classical symmetry, in other words, group symmetry. So just group symmetry, as we're familiar with, will be a special case of quiver symmetry in this way, and that will be clear in example 3. But classical symmetry is a special case. What I also want to highlight is that sometimes, in many examples, the network structure itself will be completely equivalent to the presence of some quiver symmetry. And I will go through plenty of examples now to show you exactly what I mean. So let's start with subnetworks or maybe node dependency. So node dependency, here's the exact same example that we looked at before. But in this case, instead of R2 and R, I've just taken 2 vector spaces, and here I've taken that same vector space, but this is still heuristically the same map. And what we saw, or what I claimed, was that having an ODE here and an ODE here, such that they together make a quiver symmetric system, was equivalent to putting a system like this here and then putting that component over here. So that was equivalent to this sending solutions to solutions. So in some sense, it's something you sometimes see with quiver symmetry. This sending solutions from the ODE here to the ODE here puts no restraints on this guy, but it puts a restraint on this guy, namely that x can only depend on its own variable. But that's kind of nice, because if we look at 1/2 of the quiver symmetric system, so the ODE over node 2, we see that we have essentially encapsulated node dependency. We've encapsulated that x only depends on itself, whereas the variable y depends on both. And if you recall, this form was equivalent to it being one component of the 2-component ODE that is a quiver symmetric system. So in that sense,
I ask you a quick question.
Sure.
Yes, you couldn't pick, for example, x, y goes to x plus y here, right?
Yeah, if you did that, it would change what ODE you put here and what ODE you put here. So you could do it, but you can put any linear map here, but then the tuple of symmetric ODEs can become very wacky. You can essentially create arbitrarily wacky families of ODEs.
But
if you put, yeah.
Does it deep at its core mean that there exists a further invariant subspace? Does it mean that what you're putting here in this map is a projection onto an invariant subspace of the ODE on the left?
That's a very good point. So there is no invariant subspace here necessarily. However, I think of this as the dual situation of that. So in networks, you have quotient networks and subnetworks. This is the subnetwork picture, and the quotient will actually be the next slide, or the next slide, will be corresponding to invariant spaces. So I see this as a kind of dual notion to invariant subspaces, but we will get to that example.
I see, thank you.
Yeah, no, please interrupt if you have questions, of course. So we've been able to capture this very easy example of node dependency. And what I want to claim in this picture is that you can play that game in more generality. So with a much more complicated a quiver and quiver representation, you can actually encapsulate that this ODE has the property that node 1 only depends on itself, node 2 depends on the state of node 1 and 2, nodes 1, 2, and 3 depend on each other. You can put all that information in a quiver representation in exactly the way as we did here. So this is like a map that sort of forgets about an entry. That's also what all these maps are. I will not go into detail exactly how I'm doing this, right? But there is a way, and it's very similar to what I did over here. So you can capture essentially all that direct and indirect node dependency together in a sufficiently complicated quiver. So here's the example that you alluded to, invariant spaces. So what I want to drive home here is that the presence of an invariant space is also a kind of symmetry, a kind of quiver symmetry. So suppose I have a vector space V and a subspace, linear subspace W, which is included in there, a subspace. Now what I'm going to do is I'm going to take the following quiver representation of the quiver we had earlier. Maybe the arrow is the other way around, but I'm going to take here the vector space W. I'm going to take here the vector space V, and my linear map will be X goes to X, so the inclusion, which is a linear map, right? Then if I take all tuples of vector fields, one on W and one on V, such that the inclusion sends solutions to solutions, then on the right, I get precisely all vector fields that leave W flow invariant. And as a kind of artifact, we very often have these artifacts, I get that restriction here on the right. So in other words, invariant spaces are just a special case of quiver symmetry. And of course, of most importance to us here will be these polydiagonal, right? These invariant spaces where xi is xj, these so-called synchrony spaces. But it doesn't have to, right? Just any invariant space, the presence of an invariant space is a case of quiver symmetry. But then you can play that game again and have nested sequences of subspaces that in networks typically correspond to these so-called quotients. So if you restrict to it, you find an admissible vector field for a smaller network. We call them the quotient networks. And you can put all that information in a big quiver that now captures all the invariant spaces and how they are linked and how they are nested. So all that information can be put in the quiver. So let me go to another example, which I kind of like, which really drives home how modular this construction is. So on the left here, I have a network vector field, or a network. And when you kind of play with the dynamics, when you play with the bifurcations, you really get the idea that there is a classical symmetry in here, a Z mod 3 symmetry. But unfortunately, this one has no classical group symmetry. The only symmetry, classical group symmetry that this network has is the identity map. So, okay, tough luck. However, there is a quotient, so there's an invariant space corresponding to the identification of nodes 3 and 4, where you get this. Again, there's no symmetry, but there already seems to be something appearing. So this system has a subnetwork, so just a bunch of nodes that only that don't get any information back from 5. And that's this network, and that one, of course, has Z mod 3 symmetry. And we can put all that together, so in particular relating that information of the group symmetry here all the way back to our main guide that we're interested in by a sufficiently complicated quiver. And it looks a bit complicated, but it isn't at all. It's very modular. It's just what we've been doing earlier and just pasting that together. So this linear map identifies this guy as a subspace, as a flow invariant subspace of this guy. This linear map identifies this as a subnetwork of this. And then here I have the 3 self loops that are just group symmetry. So this hopefully convinces you, right? If I forget about this part, this convinces you hopefully that group symmetry is also a form of quiver symmetry. They're just self loops, right? They go from the space to itself. So in that sense, using this, you can actually show, for instance, that this kind of symmetry, this kind of group symmetry plays a role all the way in the dynamics of this bigger guy. And
Hi,
the final...
I have a
Yeah.
question. Can
Go for it.
you teach us how to find a quiver?
Yes.
It seems like it's very hard, or it's like try and error, or there is some systematic way to construct
Both
the
a bit,
quiver.
yeah. No, you're absolutely right. How to actually find this is a bit of trial and error, a bit of playing with it. But
Do you
two
have
things.
any algorithm like a motif? You build the Lego one, and then you build up, or I mean,
Well, yeah. So the modularity of these kind of constructions, that you can just paste down the relation for subnetworks and quotient networks, you just put it together in one quiver. That helps you. In the next slide, I will hint at an algorithm, which I will not spell out, but I will say that for certain classes of systems, there is an algorithm that we've written out that does it for you. But in general, this is now the name of the game, trying to find geometric properties and finding a description in terms of quivers. I don't have a one-size-fits-all description for that. It now becomes creativity, right? Trial and error.
Thank you.
But so, like I said, a lot of cases we have just worked out and you can write down. So the last thing I want to say about the examples is that a lot of network structure itself is quiver symmetry. So not just properties like invariant spaces or hidden symmetry, but the actual network structure itself can often be seen as a form of quiver symmetry. So this works for these so-called homogeneous networks, so where all the nodes are of the same type. We have generalizations, and there are a couple of things that a couple of properties that I'm pushing under the rug here. But what you do is you create a so-called fundamental network, which is the Cayley graph of a monoid. I'm not gonna give the algorithm. I'm just saying that this can be done. It's a purely combinatorial exercise. You just follow your nose, follow the algorithm, and this gives you a quiver that describes the full network structure as just equivalent to some kind of a quiver symmetry. Again, it takes me too much time to describe it in detail, but it is in our paper, center manifolds. I'll cite at the end, center manifolds of network systems. So sometimes even the network structure is quiver symmetry. So now I need to tell you why we want this, right? Why are we introducing quivers? Why not just stick to networks? So for that, we're going to go to the main result. I need a little bit of algebra, really a smidgen of algebra to describe this. So given a quiver representation, right? So R is a quiver representation, has vector spaces and linear maps for all the arrows and for all the vertices of a given quiver, right? Vertices, arrows, and source and target maps. We define a sub-representation of R as simply a choice of subspace for every vertex. So for every vector space that we had, we choose a subspace. But we want that every linear map, when it's well defined, every linear map sends the right subspace into the right subspace. So when you have that, this sub-representation gives you a representation in its own right. So this is why we call that collection of views, we call that a sub-representation. So here's an example. This was that representation we had before. I pick any constant, and then I can take this subspace, just everything of the form x comma cx, so maybe x and 10 times x, which sits in R2, so it's a subspace. This is a subspace, but it's just the whole thing, so it need not be proper. And then you can show that this map trivially, sends elements of here and here. So this is, there's almost nothing to check that this is a sub-representation. Of course, it sends elements of here and here because I take the full space. Another slightly less trivial example is this one. So where the x coordinate is 0, and here I take just the 0 space. But if I apply this linear map to here, I just send any element to 0, right? I pick out the x component. So it restricts, it sends this subspace to this subspace. The infinity, you know, is just because it's like C, but where C is 1 over 0, right? So these are two examples, or infinitely many examples, of sub-representations. And the nice thing about these choices is actually that component-wise, they sum up to the full representation, you know, for any fixed C. And when that is the case, we say that R is the direct sum as representations. So now we have a direct sum as representations because it's component-wise. So why am I interested in that? The big theorem, back to center manifold reduction. Suppose we have, right, a quiver representation, and a quiver symmetric system. So recall, a quiver symmetric system is a choice of ODEs for each vector space. And I'm writing each of these ODEs already, you know, as a linear part in higher order because I want to do center manifold reduction. Since I have a linearization for every ODE, each of these linearizations gives me a center subspace and a hyperbolic subspace, right? Recall from center manifold reduction. Then the first lemma that we need, again with Poppenink and Sir van der Gracht, is that if I take the center subspaces for every vertex, right? So in every linear space, they together form a subrepresentation, and this same for the hyperbolic ones. And what's more, you know, they are a direct sum, they give a direct sum decomposition of your representation. And this, of course, follows from the fact that since it's a quiver symmetric system, you have all these relations between the AI, right? They send solutions to solutions, and that has strong consequences for the linear part, and in particular for the center and hyperbolic parts. Okay, so far so good. So now suppose each system in this family of ODEs satisfies the conditions of our previous theorem on center manifolds, so that we can speak of the center manifold. Then we have center manifolds for each ODE, so for each vertex. And then the big theorem is that each of these symmetry maps of the quiver representation restricts to a map from the right center manifold to the right center manifold. So they map center manifolds into center manifolds. And if I then project down to look at only the dynamics on each of the center manifolds, it will be conjugate to just a quiver symmetric system on this sub-representation. So we'll give a picture in a minute. So, but in a nutshell, quiver symmetry survives the reduction. So here's the big picture that I should have given. You know, this is what the theorem says, this picture. You have a quiver symmetric system, so you have a bunch of ODEs, a bunch of linear maps that send solutions to solutions. You identify center manifolds. Then you just restrict your attention to the center manifolds, and they together form a new quiver symmetric system on this sub-representation that was all of the center subspaces. So quiver symmetry survives the reduction, and that also means, therefore, that all the aforementioned properties, right, all this node dependency, all this invariant spaces, sometimes the entire network structure itself, in a sense, survives the reduction. So we have essentially proven that indeed all these properties survive center manifold reduction. And the same holds true, by the way, for normal form. So we have also shown that normal form can respect quiver symmetry, Lyapunov-Smith, and in a sense, phase reduction, even though that's quite a different setting.
Very good. But sorry. Could
yes.
you explain again about these 6 pictures?
Yeah.
The previous slide. Yeah. Explain again each picture. What does each picture arrow mean? So you have a very large. Okay, please.
This one you mean, or
No, the picture. Next slide.
um,
Here. Yeah. Can you expand the picture and the arrows? What do they mean? I a little bit confused.
yeah, no worries. No, this stuff is always the first time you hear it. So we have a quiver equivariance system. So we have a bunch of vector spaces and a bunch of
Yes.
linear maps in between.
Yes.
And this is, so we have a bunch of ODEs. I'm going to do center manifold reduction for each of these ODEs. So they each give me a center manifold.
Yes.
And now I claim that these linear maps that I had for all these, from the quiver representation, it will turn out that they actually send a center manifold, at the source of the arrow into the center manifold at the target of the arrow. It always does that. And then when I have a center manifold, I can always project down to get, to conjugate to a vector field on the center subspace. And if you recall, the center subspace forms a subrepresentation. So each symmetry map maps these components, these subspaces to themselves, right, to the respective ones. And so what I have now is if I project down, I have a bunch of ODEs on all of these center subspaces, and I still have maps that send these center subspaces to themselves. And I claim that this reduced dynamics is now again quiver symmetric. So it again maps solutions to solutions. But of course,
and in particular, you mentioned that the groupoid viewpoint is a special case of yours. So the groupoid symmetry also respect the center manifold reduction. In particular.
Yeah, so I think that groupoids are. There are many results about it that I cannot replicate as far as I know. But yeah, I think groupoids are indeed a bunch of linear maps to different.
They have
and
an
they
inverse.
want to, and they want to send solutions to solutions. So this would be indeed a proof that groupoid symmetry is also preserved in center manifold reduction. Yeah.
So can I interpret your result as you want the center manifold reduction to be respected by some symmetry, and the quiver symmetry is the biggest one, it's the most general one.
Yeah.
So the center. Do you expect there's a more general one, or it's already the ultimate symmetry?
I wouldn't be surprised if there is.
Because you see, suppose I am the groupoid man. I think groupoid is already very good. Yeah, groupoid can respect the center manifold with that. But now you are telling me, no, you are still too small. I am bigger than you because quiver can be more general than you. Then do you think that is another guy who is bigger than you? Say, I'm Quentin.
Well, so the work on groupoids is absolutely amazing. I'm not going to downsell that, but I do think that this is as far as like, you can push the idea of classical symmetry. So just linear maps sending solutions to solutions. I think this is the furthest you can push it because, right, I don't need any closeness conditions under the linear maps. They need not be invertible. They need not even go from a phase space to the same phase space. So, well, if you can think of an even further generalization, please email me because then I'm curious if I can capture it or do something with it. Yeah,
I think it's already very good to discuss maybe my my feeling here. Maybe I can rephrase my feeling in another way. Can you have a minimum model of the symmetry system? Like, can you find a set of axioms, very, very simple, and based on this, you can try to generate.
yeah, that's a
have
very
this
interesting
axiom,
question.
like, but this idea is from my friend Alejandro, not from me, but we discussed. But maybe my interpretation is not yours. But
I don't know. I don't know what you just said.
Okay. Yeah.
Yeah, I definitely don't want to claim that I have now that this is the end all be all of symmetry. Who knows? Yeah, who knows what's out there, right?
Okay. But very good. I see.
Thanks.
Good.
So we are at about an hour. Do you want to?
No, please wait. I mean, as you wish. There's no time limit, but if you are tired, tell us. Then we will.
Oh no, it's okay. So I can finish in 10, 15 minutes, but it's up to you.
Okay,
It's
okay.
about the schedule of the seminar.
Yeah,
Right?
10, maybe 10 or 15. Yeah. Okay, thank you.
Okay, perfect. Yeah, because
Amazing talk. Yeah.
oh, thank you. So so this is kind of a nice wrap up of this result. Hence my question of I can wrap it up as well. However, I feel like, you know, when you look at this, we felt there was more that we can do. And instead of just, you know, instead of just the result that all these structures can be preserved, now, of course, we want to ask what representations can this subrepresentation EC be? In other words, we're getting to classification of bifurcations. And it turns out we now have some algebraic machinery at our disposal. And of course, if there's anything that algebra is good at, it's classification results, right? Just having a list, an exhaustive list of everything that can happen. So the question I want now is, what representation can this reduced system live on? So a smidgen of algebra. So given two representations of the same quiver, and this is really going to mimic what you're used to for groups. We say that these two representations are isomorphic if there are linear invertible maps between all the vector spaces living there, such that there of course has to be a compatibility such that you have such a commuting diagram for every arrow's linear map. And I'll give a schedule in the next, I'll give a commuting diagram in the next slide. So this has to hold for every arrow. So here's an example. Recall that we had these representations, these sub-representations for any C and every D. And then this is just the map. But what I can do is I can just take the first component, replicate it. This is an invertible map. Here I just put the identity. And then you see that this diagram commutes. So in other words, if I take this linear map and then this linear map, I get the same outcome as if I take this linear map first and then this linear map. So this has to hold for every arrow, but we have only one arrow. And these have to be invertible. So this shows that these two quiver representations are isomorphic. So that's nice because we have infinitely many, right? We can pick C to be anything, but they're all isomorphic. Right, so they're isomorphic representations. So now let's look at the other one that we saw, this other subrepresentation. I can put an invertible map here, but I cannot put an invertible map here. So this is already failing. So these two can never be isomorphic. So if the dimensions don't add up, right, point-wise, if the dimensions are not the same for every vertex, then there's already no hope of the representations being isomorphic. But conversely, dimensions could be the same in general, but them still not being isomorphic, right? But okay, here it's hopeless. Another little concept that we need, you'll be quite familiar with as well. If you know group representation, you must have heard of irreducible representations. This is the correct generalization in the context of in the context of quiver representations. So we call a representation indecomposable if it's not identically zero. So I don't want literally every vector space to be zero, right? That is like prime, for the same reason that one is not a prime number, that would be pedantic. So it's not really everywhere identically zero. And I cannot write it as the direct sum of subrepresentations unless I choose one to be zero and one to be the other, right? So unless trivially. So then we say that it's indecomposable. So again, some examples, it's quite easy to see that these two, or these infinitely many representations that we looked at, that these were all indecomposable representations. So why are we interested in indecomposables? For exactly the same reason that you're interested in them in group representation, because we also have a Kroll-Smith theorem, or Kroner-Mack-Smith theorem. So what does it say? It says that every quiver representation, say non-zero quiver representation, but can be written as the direct sum of indecomposable subrepresentations. So this is the first part. This part is easy because you can easily prove this. How do you do that? If it is itself indecomposable, then you're done. If it's not indecomposable, split it. Then you see, are both indecomposable? Yes, you're done. If they're not, split it even further, because I want the dimensions to be finite. That at some point terminates over every node, right? Just terminates. And then I have a decomposition into indecomposables. So that part is quite easy to prove. The other part is a bit trickier. It's not incredibly hard, but the other part is a bit trickier. The decomposition is unique in a special way. In the following sense, that if you have an other decomposition in indecomposables, then necessarily n is k, so it's the same amount. And after reordering, they're not the same per se, but they're isomorphic. So up to isomorphism type, the decomposition in indecomposables is unique. This is the same as for groups, right? So here's an example quickly. Recall that we had this quiver representation that we were interested in. We pick a C, just one C, and then we found a decomposition like that, but both were indecomposable. So this is a decomposition into indecomposables. Now I told you it's unique, but I can choose C to be anything, but that's not a problem because UC and UD were isomorphic, as we saw earlier. So this does not go against Krill-Smith. They're different decompositions if I take another C, but component-wise, they're isomorphic. So that was all that Kronemark-Smith said. So now we can actually quite easily answer our question: what representation can the subrepresentation EC be? So here's the corollary, really very easy corollary. Up to isomorphism, there are only finitely many options for EC, and by the way, for EH as well, for the center subspace. You know, the sub-representation of center subspaces and the sub-representation of hyperbolic subspaces. And why is that? Proof is very easy. Take any EC and any EH and decompose it in some way into indecomposables. Then that gives you a decomposition of R, because we know that R is a direct sum of these two. So this is a decomposition into indecomposables of the representation that we started with, R. But this decomposition of R is unique up to isomorphisms. So in other words, EC and EH can be fully described by simply distributing the indecomposables of R across them. So you just say you have a decomposition of R. You just have to choose which ones go in EC, which ones go in EH, and that is up to isomorphism, all the options for EC and EH. There, you know, that you can count that there are maybe, I don't know, 2 to the power k plus L ways of doing this, finite at any rate, right? And maybe even less if some of these are isomorphic. So up to isomorphism, there are only finitely many options. So that's, of course, great news for classification. So now we can do the theorem that we promised, right? So this, and hopefully at this point you are convinced that we can do this for more complicated examples. But why do that, right? Why make it easier for this presentation? Why make it harder for this presentation? So we started with a feed-forward system, and then I said that after center manifold reduction, the system is isomorphic to this always. So in other words, feed-forward structure is preserved. What's the proof? Very easy. You make the remark that you have a quiver, and right with some kind of a quiver representation, the one that was our running example. Then you note that if you write down all the quiver symmetric systems for this particular quiver representation, then on the left you get precisely the vector fields that we were interested in, the feed-forward ones. And on the right you get some auxiliary thing that, you know, corresponds to a subnetwork. We're not too interested in it, but sure, it's out there. We're mostly interested in this part. Then you note that EC, by the previous argument on the classification of subrepresentations or complementable subrepresentations, you know that EC has to look like this, because we know that there are up to isomorphism only 2 indecomposables. And if we make some nice choice, then this is what it looks like. Maybe a U is 0 and a V is 0, but the condition that F and G have imaginary eigenvalues actually makes that these two are both non-zero, but they may as well at this point. It doesn't change anything. Then you go again, arguing that the reduced system is quiver equivariant, is quiver symmetric. And we know all the quiver symmetric systems for this because it's exactly the same as this, but with other variables, other dimensions. It's everything of this form necessarily because it has the quiver symmetry, and quiver symmetry for this particular example is equivalent to looking like this. So now you just compare the first components, right? So the center manifold of this guy, the reduced dynamics of this guy, the reduced dynamics looks like this, and the reduced dynamics of this looks like this, but we don't need that part anymore. So comparing just the first components, we see that indeed the reduced vector field is conjugate to this guy, so feed-forward structure is indeed preserved. And, you know, again, you can hopefully believe that you can do this scheme quite easily for all kinds of other network structures, geometric properties. You just have to prove that it can be preserved. But this is an essential step in classifying, for instance, generic bifurcations in these feed-forward systems. So with that, I would like to thank you for your attention. And here are some references.
Thank you very much.
Amazing.
Yeah, you're welcome.
So I think Alejandro, you have a question, please.
Yes, I have a question about this last slide on the feed-forward structure on the center manifold. So you have these spaces U and V, right?
Yeah.
Are they? How do they relate to X and Y?
Yeah, that's a good point. So U is necessarily a subset of X because, you know, that just follows from this one. The dimension, the relation between V and Y, or V and X and Y, is a bit more complicated. But so here's the honest answer. This space has some kind of a center subspace, and it will be complicated. It will lie in there skewed and all weird. It will certainly not be, it will not be necessarily a component here times a component here. However, we know what all these center subspaces look like up to isomorphism. So this U and this V is not even necessarily a subset of X and Y, but we know that the center subspace here and here is isomorphic as sub-representations to it. So this is in a sense, this is a very nice representative of all possible center subspaces that you can have here. But we know that up to isomorphism, it's always this.
I see. I'm asking because there is a very nasty, a very slight delicacy, which is that every equation on the center manifold is feed-forward by construction, right? You could write the equation for the center coordinates, xc dot equals whatever, but it only depends on xc. And then xh dot is a function of xc.
Yes, that's correct. That's outside of here.
Where J doesn't depend on V.
Yeah, so, I see what you mean, but these two coordinates are coordinates of the center, on the center subspace, so there is indeed another layer, which is the fact that this drives EH. But these are coordinates on the center subspace, so we're not feeling the hyperbolic part here anymore.
Yeah. Thank you. Yeah, I see.
Nice. Yeah, but it's a bit like it. Yeah, thank you. Yeah.
You're welcome.
Now before I ask question, I want to check my understanding. Okay, and please you can tell me answer if you have time. Okay. So
yes, exactly. Yeah, sounds good.
Group symmetry is when all the nodes are the whole phase space X, right? And exactly. Are the same. Is that correct?
Yes,
I think symmetry in your quiver terminology.
Yeah, no, precisely. No, this is precisely correct. If you want to capture group symmetry in terms of quiver, you have only one node, right? Only one vertex and a bunch of self loops, self arrows.
Nice.
That's precisely correct. Yeah, yeah, and that's the generalization.
And the groupoid is you can have many different nodes, but their linear map are all invertible and associative, right? Associative, because they can composite.
Yes.
They have identity, but here you don't need invertibility. You don't need associativity.
Yeah, yeah. That's again precisely correct. So the way my idea or our idea to capture the groupoid formalism, I mean the groupoids in this language, is I take one vertex for just the phase space of the system, then I take a bunch of inclusion maps for all these subspaces, right, on which sort of the groupoid lives. And then you, between the nodes for all these subspaces, there were invertible maps that represent your groupoid. I think,
very good. And it's okay. Maybe can you give me an example of a network dynamics such that it cannot be explained or captured by the groupoid, but only can be captured by your Kuiper language? Is this the example?
I think this is the right example, yeah, because this is not the inclusion, so this is just, yeah, I think this cannot be captured by
I see, because it's not invertible, simply and different. And
do you think, because I noticed, well, I mean, you've only shown us this quotient example, right? But
yeah,
do you think you could have some sort of, how to say, canonical or representation of your symmetry quiver, which is a family of isomorphisms together with easy quotients, so to say, right? Because yes, you could have a more complicated quotient, but somehow you should be able to write this as a composition of projection and isomorphism or something like this.
right. That's a good point. So there is a result by Spivak and et al., I think, and Lerman and de Viel, that says that, well, any of these maps. So okay, I should maybe back down a bit. So these maps that we use, these linear maps, they come from certain they almost always come from certain constructions at the level of the graph. So these are called graph vibrations. They're manipulations of the graph, but they induce these linear maps. So it's not a necessity, but in all of our examples, these linear maps, they come from just looking at the coefficients of these so-called graph vibrations. And they show that every graph vibration is always the composition of an injective one, which I would call a subnetwork, the identification of a subnetwork, and a surjective one, which I would call the identification of a quotient network. So each of these, they have some sort of a classification of, or the other way around, right? But a composition in some order. So they definitely have results there that at the level of the graph vibrations, which is what 99.9% of these linear maps are found by, have these decompositions. So it's certainly not hopeless to make this more systematic. The problem is, though, there are many quivers. Quite often there are many quiver representations that capture the same structure, right? I mean, pedantically, you could make an identity map here, right? But also many more less pedantic examples. So it's the quiver that captures the network structure is not unique. But we are hunting for systematic ways of, if this is your network structure, here's the quiver that gives you the structure.
I see. Nice.
And I don't know whether this is possible, but there's a field so-called bifurcation without parameters.
Yeah.
You know this, right?
I am For example, not
like
Speak. Yes, you were saying.
Oh, sorry. No. I thought no. Please continue your question. But yeah.
Yes. If you have a bifurcation with parameter, you have this. So the parameter is lambda, then you have this artificial lambda dot is 0. Okay,
Yeah.
because lambda is a stationary parameter. But you can also consider lambda dot is not 0, but it finishes along some manifold. And usually this setting happens when you fix all external parameters, but somehow you have a line of equilibrium, and due to some symmetry consideration, you have this line of equilibrium or manifold of equilibrium, and along the manifold, your normal stability property changes at some point.
Yeah.
And this is so-called bifurcation without parameter, because your lambda dot is not 0 anymore. And I am not sure, maybe I am curious whether this quiver symmetry can be applied to such a setting, and yes. And recently, Alejandro and I, we apply this technique together with a classical bifurcation. We call this a hybrid bifurcation. Bifurcation without parameter first, and then there's an external parameter mu, and the mu induce a classical bifurcation, and we can find periodic orbit. Okay, from the finishing of the line of equilibrium. And yeah, because today you mentioned your quiver representation with the bifurcation with parameter, and I am curious whether you can also do that for the setting without parameters. Yes.
Yeah, so I think I even saw your paper come by on my research gate, and my first reaction was to, I haven't read it yet, I must admit, but my first reaction was, oh, this might work. Yeah, this because it's so geometrical. This stuff only needs the right linear map sending solution to solution. So I think I have very high hopes that this works as well.
There's a fundamental question, in my opinion, which is the requirement of applying the bifurcation without parameter technique is you have to have a manifold of equilibrium at the first place.
Yeah.
But if you have a very large system, how can you guarantee there exists such a manifold? I mean, it's in general, I think it's not easy. But Alejandro and I, we somehow believe that symmetry can help. Maybe,
no, for sure.
Maybe can we provide some very general weak sufficient condition to guarantee such an existence of manifolds? And maybe, I mean, this is I think this is interesting. Maybe really
no, for sure. My first idea to play with these things was to just have the fully synchronous space be the manifold of zeros. And in a sense, the fully synchronous space has its presence guaranteed by quiver symmetry. So at any rate, by symmetry in this formalism. So
but this fully synchronous space, this fully synchronous space can be guaranteed. I mean, it's a little bit artificial, right? Because you have a very large system. How can you find synchronous space? I think this is the same question I asked. Like, how do you know? I mean, maybe no. Maybe I am too demanding.
No, don't worry about it. No. These are good discussions. No, I mean, the thing is, a manifold of zeros, you need some kind of a condition, right? You need some kind of because in general, of course, as soon as you have internal dynamics for the nodes, you will not expect any manifold of zeros except for a zero-dimensional, right? So you need to put some kind of, but I think that if you have a network structure, then with all identical cells, then the fully synchronous space is invariant, and then it's only one condition, for that to be the trivial dynamics, to be all zeros. But of course, another way to go around that would be a modeling assumption. But well, yeah. So those are my first thoughts about these. Really, just quickly thinking about it, of course. But that would have been the first thing I try, and I think it's motivated by questions people ask and even models, right?
Yeah. Okay.
I guess the same problems are with slow fast systems, right? I've also certainly been thinking about, can I do this for slow fast systems?
Yeah.
And there you also have this degeneracy often.
Yeah. But there's one remark, which is the slow phase system, the single perturbation system is not bifurcation without parameter.
No, right.
It's bifurcation with parameter, and this parameter is the separation of the time scales. Yes.
Right.
But maybe with this single perturbation, you have additional structure. I don't know. Yeah, I mean.
Yeah, they might just have they might just provide the motivation for having a system with a family of zeros. Yeah, but of course it's not the same field, but they might help us there.
Yeah, I see. Interesting.